Hello everybody. I'm sorry again I cannot do the class online. I would prefer that, but I have again restrictions with my data allowance, so I had to buy a new contract, but it didn't work the way they said it would work, so now I'm still obliged to do things not in real time. Okay, what I have done for this, which is going to be the last course about energy, I have added 5-6 exercises to the course because I had this feeling that it was missing exercises, and today we are going to do these exercises. Okay, so the new version of the course is available on Classroom. You have the entire course, but it has only changed after page 32. I mean, there is an additional drawing on page 31, so you can print it, and then we have these new problems on page 32 because the problems which were there were not nice. I mean, I didn't like them. Okay, first exercise, we apply a motor power of 3000 watts for 10 seconds to move a car of 1.2 tons. Let's write all that. Okay, so the power is 3000 watts. The time is 10 seconds. Then what else? What do we need to collect? The mass is 1200 kilos. The road is level and the car accelerates from standstill to a speed of 21.6 kilometers per hour. So let's immediately transform it by dividing by 3.6. 21.6 divided by 3.6. This is 6 meters per second. Okay. Good. Now we have all our data, and what do we need? To know? Okay. What do we need to do? First of all, there will be an energy which is consumed by this car. Okay, and which energy is consumed? It's the power of the car times the time. So the energy consumed or used is going to be the power times the time. So this is 3000 times 10, and this is therefore 30,000 joules of energy which this car has used. Now, how much mechanical energy is the car carrying after this acceleration? This is something different. Okay, the road is level. The car, by being set into motion, has acquired only mechanical energy, kinetic energy, and this kinetic energy is 1/2 mv square. So it's 1/2 times 1200 times 6 squared, and so this is 600 times 6 times 6, which gives us 21,600 joules. Okay, so this is the energy which is useful. Okay, you see, of course, that the useful energy, the energy connected to the motion of the system, this energy is smaller than the energy which has been given to the car. Okay, so there are losses due to internal friction, etc., etc. Okay, good. So we have the energy consumed, it is this one. We have the energy which is useful. How much energy is lost? So the energy is lost is the energy which is used minus the energy which is useful. So it's 30,000 minus 21,600, which is 8,400 joules. Okay, and now we want to know the efficiency. As you know, the efficiency is the useful energy over the energy used. So here we have 21,600 divided by 30,000, and that gives you that gives you numerically 0.72, which is 72%. Well, this is not the usual efficiency of a car, at least of a thermal engine. Okay, so this might be you may, if you want to represent yourself this problem, you can consider a car, an electric car with a motor of 3000 watts. I guess it's a bit small for an electric car. This is not a Tesla, this is something smaller. Okay, it has this electric engine, but then the power which is transmitted to the wheels, the energy which is transmitted to the wheel, is of course less than what the engine produces because of all the internal frictions in the system. Okay, good. Let's go to exercise 2, which is almost as delightful as exercise 1. Okay, it's very easy. Try to do it, and then we will do it together. Take your time, try to do it, come back. Okay, let's assume you did it. What is the kinetic energy of a car of weight 1 ton? So the mass is 1000 kilograms. That drives at 72 kilometers per hour. 72 kilometers per hour is 20 meters per second. Okay, so the velocity is 20 meters per second. How much work does it take to stop this car? This is another question. And then on 75 meters. Okay, now we need only these two to compute the kinetic energy. So it's 1/2 times 1000 times 20 square, which is 400. 400 divided by 2 is 200. And so this is 200 with 3 more 0. It's 200,000 joules. Okay, this is the kinetic energy of this car. Now, how much work does it take to stop this car? Well, as you know, the kinetic energy plus the potential energy, okay, they are constant in a conserved system, but if there is an external force acting on the system, these will change. Okay, here we are we are horizontal, so the delta K and delta U, they are given by the work of motor forces plus the work of friction forces. I recall you that the work of motor forces is positive, so it makes K increase, for instance, because here U is 0. Okay, and the work of friction forces is negative because of the angle between the force and displacement. And so here we are going to have a delta K which is negative, so K final will be smaller than K initial. Okay, you have a car which here has a certain K initial, and this K initial is 200,000 joules, and we are going to act on it with a force which is in the direction opposite to the displacement. This is the friction force, which is in the direction opposite to the displacement. And when the car arrives here, the final K is 0 joule because it's stopping. There is no question about potential energy because we are on a flat road. Okay, so the delta K is K final minus K initial. K final is 0 minus K initial 200,000, so the delta K is minus 200,000. And what this equation tells us, since we have no motor forces, it tells us that this delta K has to be equal to the work of the friction force, and the work of the friction force is given by minus the friction force times the distance y minus, because between the force and the distance there is an angle of 180 degrees. Okay, so how much work? Okay, how much work is needed? The answer is this work has to be 200,000 joules, because we need to cancel this kinetic energy. Okay, we need to liberate this kinetic energy in the form of thermal energy in the brake. And now if we have to stop it on a distance of 75 meters, what force should we apply? Well, we know that the force from this formula, okay, the force is delta K over the distance. Okay, so this is 200,000 divided by 75, and that gives us a force of 2,667 newtons approximately. It's 2666.6 periodic. Let's round it up at 2,667, which is quite acceptable braking force for acting on a system like that. Right? Okay. Let's go to the next one. What is the potential energy of a 75 kilo diver, not driver, when it stands on a diving platform at a height of 10 meters? Okay, let's illustrate this. We have here our diver ready to fly, and this diver is at a height of 10 meters. Now, do you want to put the 10 meters at the level of the feet? No, 10 meters, he hits the water after 10 meters. So let's say that this height of 10 meters concerns the center of mass of the diver. Okay, yeah, I mean, we could complicate artificially the problem by saying 10 meters up to here, and then we have to add 1 meter to get to the center of this guy. I don't think it's relevant. Okay, good. So what is the potential energy? The potential energy, if you remember, is given by mgh. This is the work of, this is the opposite of the work of the gravitational force when you are going up by a distance h. Okay, so mgh, the mass of the guy is 75 kilos, g is 9.81, h is 10 meters, and that gives us 98.1 times 75. That gives us 7,357.5 joules. Okay, this is the potential energy of the diver when he is on the platform not moving. Okay, what is the kinetic energy when hitting the water? Well, the energy is conserved, so the mechanical energy up here is the same as the mechanical energy down here. Up here, the mechanical energy is U plus K, but the K is 0. Down here, the mechanical energy is U plus K, but the U is 0, so U becomes K. It's a bit blunt to say it like that. I mean, the value of the potential energy at before the dive has to be the same as the value of the kinetic energy after the dive. So here we can conclude that the kinetic energy is also 7,357.5 joules if we neglect friction, which we can do for a dive of 10 meters. It's fine. Good. But we also know that this is 1/2 mv square. So from that we can conclude that V is 2 times 7,357.5 divided by the mass, which is 75 kilos. And that gives us what? That gives us 196.2 meters per second, which is obviously wrong. What did I do wrong? Well, I forgot the square root, guys. Okay, when you end up with a result which doesn't look good, ask yourself questions. So it's going to be the square root of that, and the square root of that is 14 meters per second, pretty much exactly 14.007. Okay, this is a typical exercise in which we compute some kinematical quantity based on energy. Okay, good. Let's go to the next. Please take your time to do it. Take your time to do it, and then come back, and I will explain you all that nicely, I hope. Okay. Okay, let's suppose you did it. A car of 1.5 tons. So let's write the mass 1,500 kilograms. Is accelerated by a motor force of 3,000 newtons. Okay, do this work of extracting the data and writing it with their normal symbols on your page. Over a horizontal distance of 20 meters, the distance is 20 meters. Okay, what is the work done by this force? It's not very complicated. Okay, it's not very complicated. The work done by the motor force here, it's the motor force scalar product with the distance, but since the motor force and the distance are collinear, the angle is 0, so the cosine of 0 is 1, and this is just Fm times d, so it's 3,000 times 20, it's 60,000 joules. This is the work transferred to this car by the motor force. Okay. Knowing that the car was motionless at the start and neglecting the friction forces, what is its speed after 20 meters? So how can we do that? Think a bit. Obviously similar to the previous problem, we already computed the work we gave to this car on a distance of 50 meters. Okay, so now there is no potential energy, but the final energy minus the kinetic energy are going to be equal to this work of the motor force. Okay, and of course the final kinetic energy is going to be bigger than the initial kinetic energy. The initial kinetic energy is 0 because the car was not moving. Okay, so the final kinetic energy is equal to Wm, which I can write as 1/2 mv squared is equal to Wm, and Wm we know it, it's here. Okay, so again the velocity will be just the square root of 2Wm divided by the mass. Okay, and this gives us the square root of 2 times 60,000 divided by the mass, which is 1,500. I hope I didn't do anything wrong. This is 120,000 divided by 1,500. This gives us 80, and the square root of 80 is 8.94 approximately meters per second, which sounds acceptable to me. Okay. I get you that for a moment. Okay. Sorry, it's a bit similar to the previous exercise, but okay. Okay, we have one more here. Try to do it. A body of mass 4 kilograms is going up an incline over a 15 meters distance. It's going up, okay, and it's going up over a 15 meters distance. The body is subject to the 4 usual forces, so the the gravitational force, the motor force, the friction force, and the normal force. Okay. Now we give you some values. The motor force is 30 newtons. The friction force is 10 newtons. And the gravitational force, of course, the arrows here are completely wrong. Well, not completely wrong, but you see, of course, that the motor force is much bigger than the friction force, because, of course, this guy is going up the ramp. Okay, and friction force is 10 newtons. The gravitational force, the body is 4 kilos, so we can approximate it to 40 newtons. Okay, and this for the moment we don't know. Okay, so now what I suggest for a problem like this is that we take something. Well, you have to decide about axes, x and y. Okay, so do you want to use this for the x-axis, this for the y-axis, or the horizontal? Let's say we do it like this. Okay, we choose the x-axis to be here and the y-axis to be here. Okay, so here we will have an angle of 30 degrees, and that's pretty much the only angle we need to worry about. Okay, good. So now let's start by computing the work of the motor force. Okay, the motor force is going in the direction of motion, 15 meters. So this is going to be the motor force times the distance, because the angle is 0, the cosine is 1. Okay, so this is Fm times d, and the motor force is 30 newtons times 15 meters. This is 450 newtons. Okay. Okay. Then what about the work of the gravitational force? Be careful here. This is the scalar product of the gravitational force with the distance, but now the distance, it's a vector which is here somewhere. Okay, this is the vector d. Okay, and this vector has a length of 15 meters and it follows the x-axis. So here we have an angle of 30, but here we have an angle of 90, so the total angle is 120. Okay, so I should compute the gravitational force times the distance times the cosine of 120, and as you expect, this will give us a negative result. Okay, the gravitational force, we said 40 times the distance 15 times the cosine of 120 cosine, this is minus 0.5, minus 1/2. Okay, so this is now going to be 20 times 15, which is 300. It's going to be minus 300 newton. Oh, sorry, I did a very bad mistake. I put newtons here. It's not newtons, it's joules. My God, I hope you will find in your heart to forgive me. Okay, it's joules. Okay, we have 450, we have minus 300. Of course, the gravitational force acts with a negative work because it's directed not in the direction of motion, it's opposite the direction of motion. Now, the work of the friction force is going to be what? It's the friction force scalar with the distance, but here the angle is 180, so we'll have a minus sign, and the friction force is 10 newtons, and the distance is 15 meters, so this gives us minus 150 joules. Okay, and we have a final one to compute, which I will put here, which is the work of the normal force, which is called soutien here because I took that from the French course. Okay, the normal force, well, it's always by definition at 90 degrees of displacement, so this contributes 0 joules. Okay? Okay, now this question of the net force is a bit, it's not so obvious, okay? You cannot decide what the net force is based on this drawing. Why? Can you tell me why? Because the arrows are not proportional to the values. You see, this arrow represents 40 newtons, this one 10 newtons. So it's not correct. We should do a drawing which is better than that. So let's do this drawing. Let's do it, and let's take a compass. I should have one here. Okay, we have 30 degrees. Is that correct? Yes, it's 30 degrees. So let's write here, let's draw here a ramp with an angle of 30 degrees. 30 degrees. 30 degrees. Then let's place here on the incline our mass, or maybe let's put it a bit higher, otherwise it will be on top of the text. It will not look nice. Okay, so now let's represent our forces, but obeying a scale. So of course we can take a scale of 10 newtons corresponding to 1 centimeter. Okay, so the gravitational force is therefore, let me use a nice red here. Yes. So the gravitational force is now 40 newtons, so it's going to be a 4 centimeters long vector. This is the gravitational force. The friction force is 10 newtons, so this is going to be a force of length 1 centimeter here. Okay? Good. And then what do we have? We have the motor force, which is 30 newtons. 30 newtons is therefore 3 centimeters here. This is the motor force, and this is the friction force. Okay? Good. Now you should understand where the friction force and the motor force comes from. The motor force comes from the motor. Okay? It doesn't come from the gravitational force. The friction force comes from the friction. It doesn't come from the gravitational force. It is influenced by the gravitational force, but it's not related to the gravitational force. And so in order to know how our gravitational force is affecting the system, we need to decompose this gravitational force in the directions of motion. Okay? One of the direction is the direction of motion, and the other direction is the direction perpendicular to motion, sorry. And so we are going to construct this parallelogram, okay? And we see that here the gravitational force gives rise to one parallel force which pulls the system down, and it gives rise to a force with which the system is pressing on the incline, which is this force here, which is what we call the perpendicular force. The normal force is exactly the opposite of the perpendicular force, so we can draw it. It's 3.4 millimeters, so it's going to be 3.4 millimeters here, and this is minus the perpendicular force, which is equal to the normal force. Okay, so these two forces, we don't care about them because they don't contribute to the motion. They are perpendicular to the motion. And now if we look at what's going on, we have towards the above towards the top of the incline we have this motor force only, we have 30 newtons. And now down here, what do we have? We have our 10 newtons of friction force, but we also have, and now I'm going to measure, it's 2 centimeters. How incredible. I was not expecting that. Okay, it's 2 centimeters, so it's 20 newtons. And now as a result, you see that the net force on this system is 0, because you have 30 newtons towards the top of the ramp, and you have 10 plus 20, 30 newtons towards the bottom of the ramp. So actually it's a system for which the net force is 0, and the motor force just compensates for friction and gravity. Okay, but the net force is 0, out of which you could conclude, if you had remembered the second law of Newton, that the acceleration is 0, so therefore this is a system which is going up the ramp at constant velocity. Okay, so in other words, the normal force is 0 newtons, and the work of the normal force is 0 times the distance, so it's 0 joule. And you see that the work of the net force is indeed the sum of these different works, the work of the motor force plus the work of the gravitational force plus the work of the friction force. We computed them before. It's 450 minus 300 minus 150, and the sum is equal to 0, and that makes us extremely happy. Okay? Good. Now the last one, which is a classic roller coaster problem. If we do a test one day, there will be a roller coaster in that. It's normal. Okay? A roller coaster train, do it first. Do it first, stop the video, do it. A roller coaster train of mass 3,000 kilos is accelerated from rest by a constant force of 8,800 newtons. Okay? So here on this car we have a motor force, the value of which, the intensity of which is 8,800 newtons. Okay, and the distance here, the d, is 12.5 meters. Assume friction is negligible. Question A, what is the velocity of the car at the end of the ramp? Let's try to do it nicely with formulas. Okay, we know that the kinetic energy, the delta K, the increase in kinetic energy, is equal to the work of the motor force. Okay, we know that this delta K is going to be K final minus K initial. Okay, and K initial is 0 because it starts from rest. Okay, so finally we have that K final is equal to work of the motor force. K final is 1/2 mv square, and this is equal to Wm, so the work of the motor force, which is the motor force times the distance, right? And now if we want to compute the velocity, we just need to extract the velocity from this formula, so we get that v square is equal to Fm times d. This is divided by 2, so we multiply it by 2, and this is multiplied by m, so we divide by m here. And now if we want the velocity, I erase the square and put a square root, and voila, that's it. Okay, and so this is now the square root of 2 times the motor force 8,800 times the distance, which is 12.5, divided by the mass, which is 3,000. Okay, and if you compute this, oh, I got somebody calling me. Not now. Okay, sorry. Oops, sorry for the interruption. So this computation gives us 8.56 meters per second at the end of the propulsion ramp. Okay, 856. So here it's 856 meters per second. Good. Now, of course, you know the next question is going to be the velocity here, the velocity here, and the velocity there, of course. Okay, so let's go to the second question. What will its velocity be at the bottom of the first valley? Okay, by bottom of the first valley, I mean in this place here. This is the bottom of the first valley. So the bottom of the first valley, it's 95 meters lower than this place. So we need to add the potential energy, which is connected to this height, and this potential energy will transform into kinetic energy. Okay, so let's write the equations. The kinetic energy plus the potential energy, let's say up, at the end of the propulsion ramp, this should be now equal to the kinetic energy down inside at the bottom of the first valley plus u down. You can formulate things like that if it's simpler for you to understand. There is no friction, there is no there is an external force acting on the system, which is the gravitational force, but this force is taken into account by the change in potential energy. Okay, now what's the kinetic energy up at the end of the acceleration ramp is 1/2 mv up squared. What's the potential energy up? Now I need to take into account this potential energy. Before I didn't need, because I was on an acceleration ramp, and if there was no roller coaster behind that, that wouldn't change anything. But now I need to take into account this potential energy that the system has when it's leaving the propulsion system. Now, the potential energy down is going to be 0 because I set the 0 of altitudes at the level of the bottom of the system. So this u down is going to be 0, and the k down is 1/2 mv down squared. Okay, so it makes things quite easy. You want to compute this v down squared, and you have all these terms. So one thing you can do, of course, to start with, is to remove the masses. You see, the mass doesn't change anything. Okay, it's a free fall type of problem, and as we saw in kinematics, mass doesn't play any role in free fall. Okay, and now we can cancel these 1/2s, which are not elegant, by multiplying everybody by 2. And so we have now that v square up plus 2gh is equal to v square down. Okay, which tells us that v down is just the square root of v up squared plus 2gh, and now we can compute that. And this is what? This is the square root of v up squared. V up squared was the velocity we computed before, 8.66 squared plus 2 times 981 times the height, which is 95. You see that now the potential energy, which has transformed into kinetic energy, is added to this formula, and if you compute that, you get 8.56 squared plus bracket 2 times 9.81 times 95. Okay, and now I take the square root. This gives me 44, pretty much exactly 44 meters per second. So it's going quite fast down the hill, which is one of the goals of roller coaster. Okay, good. Next question, what will the velocity of the car be at the top of the 65 meters hill? So we are at 95 meters, we go down, we come up 65 meters. Okay, here we have 65 meters, here we have 95 meters. Okay, so we can still use our energy here because energy is conserved. We don't need to start from the energy at this point. We can. Okay, but we don't know the energy at this point. We didn't compute it. Well, we didn't compute the other one either, so it's okay. So we can either take the total energy here or the total energy here. Well, it's simpler. It's simpler to take it here because there is no potential energy, and then we will compute it here. Okay, let's say this is A and let's say this is B. So now I can write that the kinetic energy in A plus the potential energy is A is equal to the kinetic energy in B plus the potential energy in B. And let's do things in details. This is 1/2 mVA squared. VA is this velocity. This is what I call V down up here. Okay, plus UA, which is 0 since the altitude is 0. This should be equal to KB, 1/2 mVB squared, and this is what we need to determine. Okay, plus UB, which is mgHb. Simple. Okay, I could also have said, instead of that, I could also have said, if this is point C, I could also have said that this is equal to the K in C, which is 1/2 mVc squared plus mgHc. It's the same because the total energy, it remains the same over the whole system. Okay, so this I'm not going to do it because it's more complicated to compute. Therefore now I want to compute my VB square, and so again I will cancel the m's because they don't play any role. I will cancel the 1/2s and put 2 here, and so finally I have that VB is the square root of what? Of VA squared minus 2gHb. You see, now it works very well. We imagine, of course, that VB is going to be smaller than VA because we are going up a hill, and indeed now there is a potential energy term here which is going to decrease our value. Okay, so this is now the square root of 44 squared minus 2 times 9.81 times HB, which is 65 meters. Okay, and if you compute this, what do you get? You get 44 squared minus 2 times 9.81 times 65, which gives you 660, and the square root is 25.7 meters per second. Sounds okay. We had 8.56 meters per second at 95 meters of altitude. 30 meters lower at 65 meters we have 25.7 meters per second. Okay, now last question, which is a typical question. What force would it take to stop the car after the last hill at level 0 on a distance of 12.5 meters? So the situation is this: we have the acceleration ramp, then we have the first hole, the first hill, and finally the end. And here there is a braking platform, the length of which is 12.5 meters. And on this platform there is a force which acts, it's a friction force, it's a brake which acts in the direction opposite to motion and which transforms the kinetic energy of the system here into heat, okay, over a certain distance. Now I took the same distance as up here, because up here we know how much force is needed, 8,800 newtons to accelerate the system. We will see here if there is more or less force needed. Of course there will be more force needed, because the system has gone down, the car has gone down by 95 meters of altitude, so it's going to have a higher velocity here. Okay, good. So what conditions do we have here? K final minus K initial is equal to the work of the friction force, right? As usual. The K final is 0. The K initial is 1/2 m times which velocity? Well, we can take this one. We can take the 44, because this is the velocity of the cars when they are down at level 0. Okay, so this is 1/2 m vi squared, and on the other side we have the friction force times the distance. Okay, so if we want to compute the friction force, we have 1/2 m vi squared is equal to ff times d. Sorry, I've not been careful. Okay, here there is a minus because we have an angle of 180 degrees between the force and the displacement, and here there is a minus which I forgot to report. Okay, it's here. Okay, voila. So now these two minus signs, I'm sorry, these two minus signs, they cancel. Sorry, look at what I did, I was not on it. Okay, these two minus signs, they cancel, and therefore I found now that the friction force is going to be given by 1/2 m vi squared, where vi is the velocity in that point, okay, divided by the distance. Notice that the mass doesn't simplify here. The mass plays a role, because the heavier the object, the more force you will need to stop it due to the second law of Newton. Okay, there is an inertia of the mass which has to be cancelled, which has to be absorbed by the friction force. Okay, so let's compute this. It's 1/2. The mass was 3,000, if I'm not mistaken. The velocity is 44 squared, and we divide this by 12.5. How much is that going to be? It's going to be a lot. 44 squared times 3,000 divided by 2 divided by 12.5. This is 232,320 newtons. So it's much bigger, much bigger than the force you need to accelerate this guy up here. Okay, so when you are here, you need to cancel the velocity that the car has acquired here, plus the velocity it has acquired by coming down 95 meters. Okay, voila. I hope you enjoyed this series of exercise. Next week we are going to either start thermal physics, or we are going to maybe do a formative evaluation on that. I don't know yet exactly. Okay, I will also put on the side the course about energy, about heat and temperature. So please print it so we have it available for next week. Thank you for watching. Have a nice day. I'm sorry for not being able to connect. It's going to come back soon. Thank you. Bye bye.